In class today, we developed a method for solving the ubiquitous eigenvalue-eigenvector problem. The goal of this procedure is to find all pairs lambda v, where lambda is a scalar and v is a vector, which solve the equation av equals lambda v. The algorithm for solving this problem is to first solve the characteristic equation, determinant of a minus lambda I equals 0 to get the eigenvalues lambda, and then to successively plug each eigenvalue back into av equals lambda v and solve for v. We also noted that the characteristic equation ends up being a quadratic function in lambda, so that there can always be either 0, 1, or 2 real solutions to this equation. We looked at several examples in class of 2 of those 3 situations, but we did not get to a situation where the roots are complex, and this video is going to cover one such example. So the example we're going to look at is to find all the eigenstuff for the matrix A equals 0, 1, negative 1, 0. If we look at our algorithm, then the first step would be to write out the matrix A minus lambda times the identity, which is the matrix where we simply subtract lambda from our 2 diagonal entries in A, and results in the matrix negative lambda 1, negative 1, negative lambda. Taking the determinant of this matrix consequently yields lambda squared minus 1 equals 0. Plus 1 equals 0. And this gives us 2 complex valued roots, lambda equals plus or minus I. So here we have 2 pure imaginary eigenvalues. To solve for the corresponding eigenvectors, we take turns plugging them back into our definition. We'll start with lambda 1 equals positive I. If I look at the equation AV equals lambda V in this case, the result would be to be taking our matrix A, multiplying it by our unknown eigenvector, and the product of that matrix and vector should be equal to I times xy. Multiplying out the left side of the equation and equating it with the right yields y equals ix and negative x equals I times y. As mentioned in class, both of these equations should correspond to the same equation, and they do, because if you multiply the second equation here by I, then you would get negative ix equals negative y, which we can easily see is the same as this first equation. So we can ignore the second, focus in on the first. To find a corresponding eigenvector, the easiest thing to do here is just to set x equal to 1, in which case y would have to be I. And so a representative eigenvector corresponding to lambda 1 would then simply be the vector 1, comma I. And of course, any non-zero multiple of v1 would also be an eigenvector for lambda 1. A similar procedure, which we'll let you repeat as the watcher, will show that if you take lambda 2 equals negative I, then a representative eigenvector would be 1, negative I. In fact, when dealing with complex eigenvalues, the 2 eigenvectors corresponding to complex conjugate eigenvalues should also be complex conjugates of each other, which is a good way to check that you've done the right arithmetic in such scenarios.